Hi everyone. In this talk, we will consider strong diameter network decomposition. This is a joint work with Mosen Gavary. Okay, so let's begin with the model of computation. In this talk, we will consider distributed graph algorithms, where the input graph is identical to the communication network, and the communication proceeds in synchronous rounds. And one important feature of the model we consider is that the topology of the communication network is initially unknown, and each device is only aware of its neighbors initially. And what we do in each round, in each communication round, each device does the following. First, it sends a message to each of its neighbors, and then it receives a message from each of its neighbors, and then it performs some local computation. The main complexity measure that we care about is the number of rounds, or the round complexity. And there are two variants of computation models that we can consider. The first is the local model, where we really only care about the round complexity and nothing else. That is, all other computation resources, such as the message size and the local computation time, are assumed to be unbounded. The other model is the condensed model, which is basically the same as the local model, but with a message size upper bound of log n. So that's it for the computation model. So the next, what are the distributed problems that we are interested in this talk? In this talk, we will consider small diameter decompositions. There are many natural variants of small diameter decompositions that we could consider. And one of the most natural ones is the ball carving problem, where at most epsilon fraction of the vertices are removed and the remaining vertices are clustered into non-adjacent subsets with diameter at most d. And one thing to note here is that this ball carving problem presented here is actually the vertex version, in the sense that it is the vertices that we remove. And in many scenarios, it is very natural to consider the edge version, where it is the edges that are removed. And I would like to emphasize that although in this talk, we will only consider the vertex version, but all results for the vertex version can also be applied to the edge version with the same parameters and the same round complexity. Another type of small diameter decompositions that we will consider is the network decomposition, where we partition the vertices into C color classes and cluster the vertices of each color class into subsets with diameter at most d. And it is required that any two clusters in the same color class are non-adjacent. Not surprisingly, these two decompositions are closely related to each other, in the sense that there is a simple reduction from network decompositions to ball carving. So in order to compute a network decomposition, what you can do is the following. You take a ball carving algorithm with epsilon equals to 1/2. You apply the ball carving, and then the number of vertices that are not yet clustered is at most 1/2 of the set of all vertices. So you continue to apply ball carving recursively to these vertices. And after O of log n iterations, you are done clustering all vertices. So if you assign color I to the set of all vertices clustered during the ith iteration, then then this gives you a network decompositions with all of log n colors. Okay. Before we present our main results, let's first consider the applications of network decompositions. So the reason that we care about network decompositions is that it plays a key role in the area of distributed graph algorithms. Let us consider some examples. For example, network decompositions allow us to turn any sequential local algorithm into a distributed local algorithm, such as greedy coloring algorithm. Moreover, network decompositions allow us to solve a wide range of approximation problems. For example, epsilon approximation for distributed covering and packing integer linear programs can be solved in polylogarithmic rounds in the local model via network decompositions. If you want to see more examples, you can take a look at this paper by Ghaffari, Kuhn, and Mouse in Stock 2017, where they explain why network decomposition plays a key role in this area. And another interesting example is that network decompositions allow us to transform many distributed algorithms with round complexity proportional to the diameter of the graph into ones with round complexity polylogarithmic in n. This is quite intuitive because network decompositions allows us to focus on those small polylogarithmic diameter components. And in fact, there are already several interesting deterministic conjugate algorithms that are designed based on this framework. Not only network decomposition is useful, ball carving is also very useful in the conjugate model. Recently, ball carving was used in the design of a distributed algorithm for densest subgraph detection. And ball carving was also used in recent conjugate algorithms for expander decompositions and expander routing. And because these tools are extremely useful in the design of distributed graph algorithms, this means that ball carving was also implicitly and indirectly used in many existing distributed graph algorithms in the conjugate model. Okay, so now we already know that small diameter decompositions are something fundamental and important. Now, let us very quickly review the current state of the art. First of all, recall that we only need to focus on ball carving because there is a reduction. For the randomized setting, the current situation is already well understood. That is, we know that in all of log n over epsilon rounds, we can compute a ball carving in that this algorithm removes an epsilon fraction of the vertices so that each remaining connected component has diameter of log n over epsilon. So because we already know what we can do in the randomized setting, for the rest of the talk, we will focus on the deterministic setting. For a very long period of time, the best diameter and round complexity bound for deterministic network decompositions was 2 to the O of square root log n, which is given by Pankonesi and Srinivasan a very long time ago. And this remains as the best algorithm for deterministic network decomposition. This is until the recent breakthrough by Rozon and Ghaffari in Stock 2020, where they gave the first polylogarithmic round and polylogarithmic diameter deterministic network decomposition algorithm. This is considered as a breakthrough because network decompositions is very important in this area. And the current state of the art is given by a subsequent paper by Gaffari, Grunau, and Rozon in SODA 2021. However, a major limitation in their approach is that the clusters in their small diameter decompositions are only guaranteed to have small weak diameter. So what does it mean? Let me explain. There are two natural ways to define the diameter of a cluster. The first is that we can take the subgraph induced by the cluster S and measure the diameter of this subgraph. And this result is known as the strong diameter. And we can also consider the following measure. That is, we simply consider the maximum distance between any two vertices in the cluster. And this is known as the weak diameter. It is easy to see that the gap between strong diameter and weak diameter can be arbitrarily large, because if you consider a cluster that is disconnected, then obviously its strong diameter is unbounded, but its weak diameter can be very small. Okay, so now we know the difference between strong and weak diameters. So what is a weak diameter ball carving? It turns out that this notion is actually quite complicated, but let me explain it carefully. Gaffari, Grunau, and Rozon gave a deterministic algorithm that takes only polylogarithmic rounds to compute the following decomposition in congest. In this decomposition, at most, epsilon fraction of the vertices are removed, and then the remaining vertices are clustered into non-adjacent clusters, meeting the following conditions. First of all, each cluster is associated with a Steiner tree where all vertices in the cluster appear as terminal vertices of the Steiner tree. And then the diameter of the Steiner tree is at most O of log n squared over epsilon. And then each edge belongs to at most O of log n Steiner trees. And the reason that this decomposition is of weak diameter is that this Steiner tree diameter upper bound implies that the cluster C has small weak diameter. Now, a natural question to ask is it necessary that we work with such a complicated definition? And is it possible to have an efficient algorithm that compute a strong diameter ball carving? The answer to this question is yes, for the case of the local model, because there is already a well-known reduction from the strong diameter case to the weak diameter case in the local model, and it is quite easy. But unfortunately, this reduction requires very long messages, so this does not work in congest. And so the major question that remains open is the following. Is it possible to have a deterministic polylogarithmic round and polylogarithmic diameter, strong diameter ball carving algorithm in congest? And in this work, we give an affirmative answer to this question. For the rest of the talk, I will briefly present our method. Our method is that we gave a generic reduction from strong diameter ball carving to weak diameter ball carving. The idea is very simple. We want to iteratively refine the clustering using a weak diameter algorithm for O of log n iterations. In order to implement this idea, we need to make sure that the size of a cluster is reduced by 1/2 after each iteration. In order to satisfy this goal, we apply the following strategy. We will perform a ball growing and carving from the largest cluster S, and we cut it from the graph and include it into the final clustering. What does this mean? It means that this will ensure that each remaining cluster has at most 1/2 of the vertices because the largest one is already removed. And then we can recurse on each and then we can simply recurse on each connected component of each remaining cluster, and then all of log n iterations is enough. So if we apply this reduction to the current state-of-the-art WeakDiameter ball carving algorithm, we obtain a new ball carving algorithm that is StrongDiameter. However, our method has a drawback as it worsens the diameter bound by an O of log n factor. To mitigate this, we provide a different reduction that turns any StrongDiameter ball carving algorithm into one with a diameter bound of log n squared over epsilon. So this means that we are able to get a StrongDiameter ball carving algorithm with a diameter bound that matches the state-of-the-art diameter bound for the WeakDiameter setting. So to conclude this talk, let me discuss some open questions. First of all, I would like to know if it is possible to further improve the diameter bound and the round complexity bound. So we know that this log n squared over epsilon is the best diameter bound for both the weak and the strong diameter setting. And in our paper, we also provide an explanation for why this is the limit of our approach. And I would also like to know if there are any applications of StrongDiameter decompositions. So for applications that use small diameter for routing purpose, WeakDiameter decompositions are enough. So I would really like to know if there is any example where we really need each cluster in the decomposition to have small, strong diameter. And so that's it for my talk. Thank you for your attention.